There you go, boom. All right. Now, here's what I would like for you to do. Please turn the lids of your laptop halfway down, please. Turn the lids of your laptop halfway down. And before we proceed any further in today's class, we are going to have a warm-up with branching hardware. Now, these are the pieces. These are the Lego pieces that we would need to build our data path. We'll require our ALU. We will require our multiplexer to avoid contention. And then there's instruction memory, obviously, from where we would need to fetch the instruction. We would need register file, where we would read the register values and also write to the register. We have our program counter, which holds the address of the next instruction that needs to be fetched. And that goes into the instruction memory. We have our data memory. If we are using load or store word instruction, then we would need to use the data memory. And then some other components like a standalone adder, perhaps, because we do not need to replicate this clunky ALU unit all the time. It's a dense piece of hardware, this ALU. So if you just need to perform addition for one specific purpose, and you know that you are always going to perform an addition, why not use a simple adder? Why to replicate ALU unnecessarily? And of course, we have our implicit clock, where at the positive edge of the clock, our instruction gets executed. And at the next positive edge of the clock, the instruction would have successfully completed. And therefore, we are dealing with what we call as the single cycle processor. What I would like for you to do is discuss with your partners, work with each other, and try to develop the branching hardware. Now, this is what you need to focus on when you work on branching hardware. Your program counter normally increments by 4, right? Every time when I need to go to the next instruction and there's no branching involved, I just need to increment program counter by 4. However, if there's branching involved, then the program counter goes to some other location. And that location happens to be PC plus 4 plus the sign extended version of the branch address, which is shifted by 2. So the immediate field that you see, that's the 16-bit immediate field, that's your branch address. That is sign extended. It is shifted right. It is shifted to the left by 2. Essentially, you're multiplying it by 4. The reason you do it is so that your program has a wider reach with regards to branching. You're able to branch to farther location. And that needs to be added to PC plus 4. So please discuss with your partners, work in groups, and decide on the branching hardware. And I kind of give you the hint here as well. These are the Lego blocks needed. Sign extend, shift left by 2, adder, and a multiplexer.
So no data memory, no register file, no.
Well, no, not quite, because those are already there. What you can do is you can assume that ALU has generated a signal which will decide if the branch has to be taken or not.
Okay.
Logic. Okay. So we are dealing with BEQ instruction, right? Okay. What is the
That's where the max will be.
So the instruction is BEQ. So ALU produce a 0 flag. It will be set to 1 if RS and RT are equal to each other. All right. Okay. Yeah. So there are two possible inputs, right? One is PC plus 4 plus sign extended branch shifted left by 3, and the other one is PC plus 4. How about we focus on the hardware of PC plus 4 plus sign extended branch address shifted by 2?
Two different inputs, meaning max, right? Max
Yep.
decide what
Isn't it cool to say mux?
What's the true name?
Multiplexer.
The shift, that's right. Yeah.
All right, you have like 2 minutes to finalize. Honestly, okay. So here's one. So we need to produce some items, right? So this is plus 4 plus sign extended branch address shifted by 2, right? So let me ask you this question. If you have those Lego blocks available, like sign extended, shifted left by 2, adder and all of those. So the branch address is your last 2 bits of your and I need sign extended. So first, where should it go? Which Lego block? Sign extended, right?
So
And
one
whatever
pack
comes
is
out,
this, one doesn't.
that is added to PC plus 4. So where should the sign extended branch address go next?
So zero
Sign
flag.
extended shifted by 2. Well, first you did sign extension, right? Okay. After sign extension, what's happening? Well, sign extended is actually shifted.
But stop you see the plus four now.
That goes to the unit shift left by 2. And whatever you get, that needs to be added.
Yo.
So what other units you might do? Okay. And adder. Exactly. Right. Okay. So this is your new piece. There's a branch. Right. But at the same time, if there's no branching, CC has been given by 4. So think of it as 2 individuals. PC plus 4 and PC plus 4 plus sign extended branch address shifted by 2. Whether they're branching or not, one of them has to pass. These two, PC and PC plus 4. Where should they go next? Good. Very good. Doing well? All right. Now let's quickly see the hardware for this. Now this is the hardware. Let me see if I can use my highlighter, right? So the laser pointer. So first, so this is your PC, right? This is your PC and it's added to 4. So out comes PC plus 4. Out comes PC plus 4. The branch address is the immediate field. It's the 16-bit immediate field that first is sign extended so that it becomes 32 bits. Then it is shifted left by 2. So now you have sign extended branch address shifted left by 2, and that is added to PC plus 4. And out comes your new PC, which is a PC plus 4 plus sign extended branch address shifted left by 2. Now, branching may not happen all the time, because what if the branch condition fails, right? And also, what if it is not a branching instruction? To resolve this, we need a multiplexer. We need a multiplexer to select between PC plus 4 so that I can proceed to the next instruction, or I can select new PC, which is the branch target address that we just computed. So this multiplexer, it is currently missing a control signal, which we'll talk about in today's class. That control signal is going to decide whether I go to the next instruction or I go to the branching instruction or the instruction specified by the branch address. So that's your branching hardware. Yes.
So the answer that you answer is upside, right? This is the answer, right?
Yep, the circle, this oval is the answer. That's the new hardware that we have to add. Shift left by 2 is essentially multiplying your branch address by 2. So when you shift the bits by left by 2, you're multiplying it. For example, consider 1, right? Let me rewind this one more time. Shift left by 2 actually is multiplying the value by 4, right? By 4, because if you were to consider a 4-bit value 0001, if I were to shift it left by 2 times, so shift once, I get 0010. Shift it one more time to the left, I get 0100 times 4. So that's what shift left by 2 is doing. It is essentially multiplying the branch address by 4, because that's how the branching hardware works. Tell me.
Okay, so there is shift left by 2 in circle, right? So it's part of the answer.
It's part of the
But the
answer.
thing that comes to shift left by 2, it comes not from the answer.
Well, yes,
So
not
how
from
should
the.
I like know that?
How should you know that? Well, this will always come here because the same unit will also be used by load store hardware, because at times when you're using load store hardware, it will be sent to the ALU to compute the data address. Yeah.
In this case, it makes sense. But like as a as a task before, like I would never guess.
You would never guess?
Because for you, it's like something that you've experienced. For you, like it's very
Okay.
easy to read. For us, it's very different.
Very different. Okay, so I'm having you to think about this hardware.
Okay.
Right? So some of the groups, they successfully identified that yes, you require a multiplexer, you require an adder. What I'm looking for is not the exact answer from you, but at least you should be 50% on your way to the answer.
Oh, okay.
Yeah. Okay. Yes, Marcos. It is still 32-bit. Yes, that's another good point. When you shift left by 2, it is still going to be 32 bits. Okay. All right. So please take next 30 seconds of your time, 30 seconds to digest the solution. This is not something that I would be asking you to develop in your exams, right? Because that's the role of a computer engineer. So when they take computer organization, perhaps they will do that there. But for you, you have to be able to explain the hardware, because you are, as a software developer, computer science and computer engineering ones who are developing the simulator or the new language, you should be able to understand the hardware and explain it and see how the instruction gets executed. And what better way than first to construct the hardware, right? All right, are we good so far with the branching hardware? All in favor? Okay, all right. Now we are going to design the control unit. We are going to design the control unit, which is the heart of our data path, right? Apart from the ALU. ALU is just one of the working units, but think of control unit as your central nervous system. All the nerves that goes to these different muscles to control it, that's what the control unit is going to do. We have used different multiplexers, and those multiplexers were missing the selection signal. Selection signal is actually a control signal. Now, when you consider data memory, let me ask you this question. Do you always read from the data memory for all instructions? No, only for read instructions you read it. Do you always write to the data memory? No, you only write to the data memory if the instruction is writing to the data memory. Same goes for register reading and register writing, right? You do not write to the register file all the time. So all of these different units, they are going to require some control unit, including your ALU itself. Your ALU also needs some control. Why? Because it can perform addition, can perform subtraction, it can perform instructions like set if less than, and a variety of other instructions. Your ALU is involved in R-type instruction, it is involved in branching instruction, it is also involved in load store instructions, right? So ALU also needs some control. In fact, as it so happens, ALU has its own control unit, which is controlled by certain bits. This control unit is going to generate a 4-bit signal. It's going to generate a 4-bit signal, which we will be not looking into too deep. Instead, we'll be deciding on the control signals needed to control the ALU control. It's a little bit complicated, and there's a reason why this is a little bit convoluted. Now, this is how the ALU control actually works, and this is just for general knowledge, all right? So don't worry too much about it. If ALU control generates the signal 0010, it means we are asking the ALU to do add. If it generates 0110, we are asking it to do a subtract. 0000 performs a logical and bitwise AND between the two ALU inputs. 0001 is going to do an OR, and 0111 is for the SLT operation, which stands for set if less than. So if A is less than B, then I'll set the ALU output to 1, otherwise I'll set it to 0. So these are the 4 signals generated by the ALU control, which actually controls the ALU. The takeaway message here is the ALU is used by these variety of instructions, the R-type, the branching, as well as the load store instructions. And this is the bottom line. And this is something that I want you to put in your notes. We are going to only worry about the control signals that control the ALU control. We are going to worry only about the control signals that control the ALU control. Okay. And that control signal happens to be ALU op. It's a 2-bit ALU op signal that you will be worrying about in your project number 4 and alpha and beta. So please write it in your notes. We are only going to worry about the 2-bit ALU op signal. We are only going to worry about the 2-bit ALU op signal. Now, this is how the ALU op is going to work. ALU op has 2 bits, right? It has 2 bits. Let's call them as ALU op 1 and ALU op 2. If ALU op 1 and ALU op 2 are 0, 0, then that means it's for load store instruction, right? Then that means it's for load store instruction, which means that ALU is going to perform addition of 2 values to produce a memory address for the load store. If it is 1, 0, however, then it is going to be for the R-type instruction, in which case I also need to look into the 6-bit function field. Now, do you remember for R-type, there is a 6-bit function field? You have OP, RS, RT, RD, SHAMT or the shift amount, and the function field. For all R-type operations, opcode is always 000, 000. It is the funct bits that differentiate between different R-type. For example, funct bits for an add is 100,000, whereas for sub it is something else, right? So when it is an R-type instruction, 2-bit ALU op is going to be 10, in which case the ALU control is going to look into the funct field to decide what to do, whether it has to do an add, whether it has to do a subtract, whether it has to do a shift left logic, shift right logic, or what have you. If a 2-bit ALU op is 01, then it is going to be a branch if equal instruction. So ALU is going to generate a flag relevant to branch if equal instruction. If ALU op is 11, then it is for the BNE instruction. What I would like for you to do is take next 1 minute to note this very important table. This table will be critical for you to decide on the control signals. It will also be critical when I give you your quiz, where I ask you to determine the control signals for a given instruction. So please note that table. What should happen when ALU op 1 and ALU op 2 are those different bits?
Is that going to be open notes or not?
Well, I would put that in your notes. If it is, even if it is open notes, You should have it in your notes.
Oh, yeah, I do.
00 is for load store, 10 is R type, 01 is branch if equal, and 11 is branch if not equal. Another important takeaway message here is ALU has its own control unit. There is one major control unit that controls everything. That generates this 2-bit ALU op, which goes into this ALU control. Here's my question to you. Why would you require a separate ALU control for ALU? What good can it possibly do? Why not have just one control unit do everything? Everything. Why to have a separate ALU control? Slow? That's a very good answer. It may cost you hardware if your main control is doing everything. Just imagine that if I were to put a two-man team or two-person team rather, and have you do an assignment. If one person is doing like everything, that's not good. But if it is shared between them, then those two units, those two persons tend to work well together, right? Similarly, by having a control unit dedicated for ALU, it's much better for our entire hardware. It results in a smaller hardware which can run fast. Additionally, this ALU control unit can evolve as you add more functionality to your ALU. Now remember, your ALU right now is doing only add, sub, and, or, set if less than, and perhaps shift left logic, shift right logic. What if I wanted to do XOR operation? What if I wanted to do XNOR operation? All these crazy things, right? So ALU will become bigger, and therefore its control unit should also get bigger. It allows us to selectively optimize our hardware. That's why we require a separate ALU unit, ALU control unit. Okay. Now, this is the hardware that we have built so far, right? What I would like for you to do is take the next 5 minutes, move from left to right, and determine what control signals are required for what all specific components. You see a multiplexer, you see a register, you see an ALU and another multiplexer, you have your data memory, and then you have another multiplexer. Go from left to right, visit each component, determine whether they need a control signal. And if they need a control signal, give them a nice name. I would like for you to discuss with each other for the next 5 minutes. Then I will randomly ask a group of students to participate and tell me the control signals required as we move from left to right. Yes, Marcos. Yes, it's going up. It's going in. Yes. You do have an ALU op signal here. But when you move from left to right, discuss with your partners, with your colleagues, to see what control units are required, if any, for these different units. And if they do require, give them a nice name. Oh, every multiplexer does need one. Left to right, the first one that is coming is the one. So just focus on that. Okay. All right. So then you just focus on that multiplexer. Now, what I want for you both to do is have a chat with each other. What that what credential and give it a name, give that signal a name. But you're right. That must be required.
Nice little name. Yeah,
So that first
one month size, controlled by all the
Because look at it, all RTs.
They all have two inputs.
But
All
it's
have
just-
two analysis.
That's the first. So that's what I mean. Okay, you have anion, you also have RT.
Yeah,
You have RT.
we don't really have flat numbers, but for the first mark. Yeah, so those one is going on. Either we can add C or add D to the marks, right?
Oh.
Yeah. Because we can do. Like, I'm not very. So yeah. It's kind of immediate. Or three dots from.
Decide whether it's a jumping, whether we're jumping right, or we're just going to the next step. The one we just next to the shift. Because you want to add instruction plus.
Or yeah, that's what. Yeah, that's fine. Private text.
Yeah, it's zero. Yes, yes, or if you jump. Check if it's a immediate. Oh, no, they don't. It's the one. So now one is all the sign exit. You see that and then branch out to one for the box. So I think that's gonna be for two strings. What about okay? So what about that? Oh, in the second, yeah, immediate or just read it. Definitely. So yeah, what is it? What is kind of doing? And then the one right here. Yeah, to the right of the screen. That's a check for load words for load word versus part time. Essentially, it is kind of selecting what should be the source for the alien number. Give it a nice name. So you know how he has alien? That makes sense. How's it going? Ramesh.
Okay. We need 4 alien control for all marks.
4 alien control? Alien control. Unit control. Okay. Well, if you have 2 lines, if you have 2 inputs, how many control bits do you need for a given box? 1, right? Because that bit, if it is 0, it will allow this guy to pass through. If it is 1, it allows that to pass through. You need a control for this. You need a control for this. You need a control for marks. All marks will require control. No, you cannot combine it.
So it's not all marks will control it?
All muxes will need their control signals.
Control
Their selector signals. All right. So please finalize your thoughts in the next 1 minute, and I will ask group of students to tell me.
Either extend and immediate, you know, is you immediate will sign extend and not. Okay.
All right, jazz hands. Okay. Now, this is the goal of this assignment right now. of this discussion. We are just deciding on control signals. We are not worried about setting them just yet. What we are doing here is just identifying what different units require what kind of control. So let's move from left to right, right? Let's move from left to right. You have your instruction memory. Instruction memory is always read. It is always read. It is never written to. So it can be a piece of hardware which is always in read mode, but never in write mode. We can develop that hardware. So it does not require a control signal. Let's talk about this mux. Let's talk about this mux. Will it require a control signal? Yes, it will. So team of Manohar and Jasim, how many bits would you require to control this mux? Just one bit, right? Yeah, just one bit, right? Because if that bit is 0, then RT will pass through. If it is 1, then RD will pass through. What that mux is doing, it is selecting the destination for the register to write. So give it a nice name to that control. It is deciding the register destination. So what would you name it? Register destination? Well, as it so happens, it is named regdest. Very good. It is named regdest. Oops. Okay, let's see who the lucky team is. How about Ben and team? We decided on the control signal for this mux. It's called register destination. Now we have this registers, right? When we have an add instruction, which is an R type, this register file has to be written. But if it is something like a store word instruction, then we do not write to the register files. So sometimes for some instruction, we write to the register file. For some instructions, we do not write to the register file. Do you think we require a control signal for registers to control writing?
Yes.
Yes. So what can you name it? Just give it a nice cool name.
Control right.
Control write. Okay. As it so happens, it's called regwrite. So regwrite signal, it controls whether to write to the register or not. So if regwrite is active, whatever write data is presented here, that will be allowed to be written to the register file. If it is not active, then this makes no sense. This line doesn't make any sense. It is blocked. Okay. Now, moving to the right, we have this multiplexer. Right? We have that multiplexer. So does it require a control signal, Corey? Yes, it will require a control signal. And this is what this mux is doing. Carefully observe. It's important for us to see right here. It is selecting between either the read data or the sign extended 32-bit immediate value. Either of them is going to become the second source for this ALU. So when that control signal is 0, the ALU source becomes read data 2. If it is 1, then it becomes this immediate field. So give a nice name to that control signal. Any name that you would like to give it. It is selecting the source for the ALU to compute. Register selector. Well, that's an interesting name, but as it turns out, the better name would be ALU source. Why? Because it is selecting what needs to be the source for the ALU, whether the read data 2 should pass through or the immediate bit or immediate field should pass through. Very good. Now let's move on to the right, and we are going to arrive now at the data memory. We are here at the data memory. Now, team of Ramesh, Gafur, and Cairo. No, just the 3. Right now, just the 3. Let's say that I have an add instruction. When I have an add instruction, what happens is RD gets the sum of RS and RT. That's what happens. RD gets the sum of RS and RT. In add instruction, do I ever write? No. But if it is a store word instruction, I need to store something here. Do I need to write? Yes. So for some instruction, I write to the data memory. For some instruction, I do not write to the data memory. Just like how sometimes I write to the register or I do not write to the register. Do you think this requires a control signal? What would be the nice name? What? Reg data memory?
Memory to reg.
Memory write. As it so happens, it is memory write. Similarly, do we always read from the memory? No. Sometimes we read, sometimes we do not. When it is a load word instruction, we do read from the memory, right? Because when we use a load word, we are loading a value from the memory into the register, so there has to be a read. Other times, we do not read from the memory. To control writing, we have used the signal memWrite. What about to control reading? Ankush, what would you name it? Memread. Very nice. Excellent. So the control signal that you will require is memread. Now the final one. So groups, please be ready because you may be the next. We have to control that multiplexer, the last multiplexer. And this is what that last multiplexer is doing. It is deciding which data to pass through for this writing into the register. Whether it's going to be the read data or it's going to be the ALU output. It is selecting one of the two to be the write data destination. That's what it is doing. So what would you name it? How about Matthew and T? Just give it a name. It doesn't have to be right. Just a name that you think is suitable. Memory to register. Okay. So let's see. Oops. Memwrite, memread. Very good. Memory to register because we are sending the value either from the memory or the ALU to the register. So we are asking that mux, hey, do you want to send it from memory to register? No? Then in that case, ALU will be written. Yes? In that case, the data that is read from the data memory is going to be written. And there is one more multiplexer sitting right up there. Do you see it? Does it require a control? Obviously, all multiplexers require a control signal. And that we will call it as the PC source because it's determining what should be the source of the program counter, whether it should be PC plus 4 or whether it should be the sign extended 32-bit shifted left by 2 added to PC plus 4. Quite a mouthful. But nonetheless, it is selecting PC plus 4.
So we chose the control signals.
We just chose the control signals,
Which created by control units.
which is going to be controlled by the control unit depending on the opcode. That's what we have done. So please make this note. All we have done right now is just decided on the control signals. We have not set them yet. We will set them for each instruction at a time. We'll consider one instruction at a time and determine what should the value of these control signals be. Okay, so here's what I would like for you to do. Please pair up. Please pair up. The person sitting to the left should explain these control signals to the person sitting to the right. Pair up. Person sitting to the left should explain these control signals, what they do, to the person sitting on the right. If the person who is explaining, if the partner who is explaining is kind of like stumbling, please, partner sitting to the right, help them. So pair up, do this discussion for the next 2 minutes.
Yeah. So in this case, yeah. So after the instruction memory, you see line goes to control. instruction 32, 26. So this line goes to control. Control units. And control units is very all the line register destination, register right, all the signals go from there. And right? I'm going so the control that we have. So that's the control unit.
Yeah.
And it connects to all one, right?
Yeah.
But we just discussed that it's not good.
No. That control unit is going to generate all of these signals. It's going to generate all these
So
signals.
technically the line goes there.
Yeah. Yeah.
So yeah, we didn't understand that it's like expensive
Well, that's why we have a separate ALU control unit.
for the daily
Or just for the ALU. Yeah. You can design a control unit and remove this guy.
Yeah.
But that control unit will be like
Oh yeah.
overloaded, like too much. It would require psychotherapy, right?
So all these lines that go to it will be either 0 or 1. Control will be 0 or 1. And what goes to the center?
So ALU off process. Get it from the control unit. No, we will get ALU off from the control unit. So ALU off is going to be 2 bits. If it is 0, 0, then it means it's a load store instruction. If it is 0, 1, then it is, I think, the R type instruction. If it is 1, 0, then it is branch if equal. If it is 1, 1, then it is branch if not equal. So depending on the type, it is going to control ALU. For example, if ALU off is 0, 1, it means it's R type instruction. In that case, ALU control also needs to look into the function. Yeah. 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 Function. Right. Yes. Yeah.
Worksheet. So on this looks for the 2 bits, right?
Yeah, that means 2 bits.
So 1 0 0 0 1 1 or 0 1
seems to be a little extended version, right?
This is worksheet.
Yeah, this is worksheet. So yeah, in that case, it will require 2 bits. Yeah.
And for us, and then in the worksheet itself, I just out of my head.
No, you will see which line needs to go through. We'll talk about it too soon. Okay? Yeah, just hold on. Okay. All right, jazz hands again. Now let me ask you this question. So, are we good with these control signals? All right. So these, well, it will get better. It will get better because there are some more exercises for you to solidify these concepts. Now, please note that this control bubble that you see here, that's the brain. That is generating all of these signals. It's generating reg dest, it's generating reg write, ALU source, ALU off, PC source, mem write, mem to reg. How does it generate? Well, it takes in the opcode. Depending on the type of opcode, it is going to generate all of those signals. For example, if it is an add instruction or if it is an R-type instruction, these registers, or rather these control signals, will be given specific value. If it is a load word instruction, these different signals will be given specific value. Now, what I would like for you to do is take 10 minutes with your peers and determine and write down the role for these different instructions, these different control signals. That's what you need to do for the next 10 minutes. And then I will randomly ask 1, 2, 3, 4, 5, 6, 7 groups about each one of them. Work with your partners and decide what these different control signals are going to do in your hardware. And this will help you to really understand the control signals. You're focusing on reg dest, reg write, ALU source, PC source, mem read, mem write,
Easy.
and mem to reg. So you need to find out what is the effect when they are 0 and what is the effect when they are 1. And here's the diagram for you so that you are able to understand. On the board, you'll see the list of control signals. These are the control signals you need to focus on, and that's the hardware in front of you. So discuss with your peers to find out what happens when they are set to 0 and what happens when they are set to 1. We have 7 control signals, so I will ask 7 groups. So please actively discuss.
Birinci max ben oradan başlayacaktım. 0 olanda seçik artı. 1 olanda seçik artı. Right.
But you know, be more specific. For example, when they write 0, I would say memory writes the signal. Memory write 1, memory write enables. So be more explicit.
To right or no? Exactly. So 0 olandan all right? Yes. Meaning that store word or okay, 30 ALU source. Also, 0 olanda. Is that
Okay, I see. It's being written. I think it's being. No, why is this?
Yeah, either you see itself. Yeah. 0 is 1 is getting sign extend. Yeah.
Oh, it's 2 portions. 2.
What else? iPad is that my soul?
Very readable.
Please don't include us. Please don't include us here. Please don't include us, teacher. We're scared. Please don't do that. What's my name?
Sorry, I forgot your name.
All right. Times are used to say. Right, zero, all right, yes, right. Yes. Well, you're gonna. It's impossible to read that.
All right.
Zero, right?
Now, please have your attention here. Okay. So we have 7 control signals, reg dest, reg write, all the way to mem to reg. And then I have assigned some teams. For example, Mo and Matt, they are going to give us information about reg dest. What would happen if the effect is 0, and what would happen if the effect is 1, and so on and so forth. The stars that you see on those names, those are the group leaders, meaning that they will take the lead and they will answer, which also means that the person on whom there's no star, they are not off the hook. They would assist with the explanation should the leader require any support. All right. So please take the next 2 minutes to organize your thoughts for your respective control signals.
So if you answer in the way like for memory read, like we'll just say 0, memory won't be reading, and 1 is memory reading. I will take it.
You have 1 minute to organize your thoughts. There's a few leaders and partners that exited the room. Don't leave your peers. All right, jazz hands, jazz hands. I hope you had a chance to organize your thoughts. So let's start to fill this table, starting with the team of Mo and Matt, and Mo is the leader. So in your own words, Team Mo and Team Mo and Matt, what would happen if I were to deassert reg dest?
So user means 0, then the RT value is the one at the second on.
Very good. If it is a 1, RD. Excellent. So here's what happens when reg dest is deasserted. RT, which is instruction 20 down to 16, it goes into the write register port. Most likely it's an instruction like load and store, or rather load to be more precise, which
And that means at least the
yes, right. And when it is asserted, which means it's an R-type instruction most likely. So RD goes into the write register port. So that needs to be written. Next, about reg write, Corey and Sam with Corey as the leader. Reg write signal. What happens if reg write is deasserted? It's disabled. Very good. You do not, well, you do not write to the register. That's the answer. Yeah, so write data is kind of blocked in that case. So reg write, if it is a 0, then that means register will not be written. If it is a 1, what will happen? It will be enabled. Very good. So when reg write is deasserted, register file is not written. But if it is asserted, then register write, then we write the register on the register write with the value in the right data. So whatever register address we have specified at the right register port, that gets written by whatever value we have presented at the right data. Now, next, ALU source, team of Anna and Logan.
If it was deasserted, then it has something data.
Uh-huh.
If it was asserted, it has something.
Very nice, very good. So when ALU source is deasserted, read data 2 is fed as a second input. However, if it is asserted, then sign extended instruction is fed to the second input of the ALU. Very nice. Next up is memread, which is UQ and Ken memread. What happened? No, sorry, PC source. My apologies. Clint, team of Clint and Tyler. So what happens when PC source is deasserted?
The new PC would be PC plus 4.
And when it is asserted?
PC plus 4 plus the sign extension.
Very good. Excellent answer. When PC source is 0, PC is PC plus 4. However, if PC source is asserted, meaning it is a 1, then PC gets PC plus 4 plus sign extended instruction shifted by 2. This will happen if there is a branching instruction. Now, UQ and Ken, what about memread? What happens when it is deasserted?
When it's deasserted, the memory will not be read. When it's asserted, it will be read.
Very nice, excellent. So when memread is 0, memory read is disabled. When it is a 1, it is enabled. Oops. Next, Ramesh and Kelvin. So Kelvin, what happens when memwrite is 1, when 0?
When the memory write is 0, it will be not be written.
Huh?
When memory write is 1, it will be written.
Very good. When memwrite is 0, memwrite is disabled. When it is a 1, it is enabled. Now, team of Jason and Vijay, mem to reg, the last multiplexer.
When mem to reg is deasserted, it's taking the ALU input value and writing that to the register memory. And when it's asserted, it's taking the data memory value and writing that to the register.
Very nice, precise answer. Excellent. When mem to reg is deasserted, ALU is written back, the result of the ALU is written back to the right data port of the register file. However, if it is asserted, then read data, the data read from the memory is written to the register file. Very nice. So this is the summary of what different control signals actually do. Different instructions are going to either assert them or deassert them, right? And that's what we need to decide, which gets asserted and which gets deasserted. So please take 2 to 3 minutes of your time to make a quick note of what should happen when they are asserted and deasserted. You may also take a phone snapshot, even that may be faster so that you can refer to it.
That's right. But there's no app. This is for the worksheet, but if you're doing add-on, would you be referring to the ALU offered as add? R-type 10 because you're kind of adding the two values?
So add-I is kind of like an I-type instruction. That's a very good question. So it would be the same.
Yo, no way.
Well, that's an interesting question, right? Because if it is 0, 1, then it is for R-type.
Yeah.
But I would use the same as load word and store word.
Okay.
Because they are kind of similar, right? Because load word, it adds a register to the immediate value. And add-I is also doing the exact same thing. So it makes sense for them to have the same ALU op. Good point.
That makes sense.
Yeah.
Yeah.
Okay, all right. Now let's have some fun. Jazz hands again, everyone. This is what we have done so far in today's class. We have seen how the branching hardware works. As computer scientists and engineers in this class, you're only focused on explaining the hardware. I will not ask you to create a hardware, so don't worry. What you should be able to do is, given a data path, you should be able to explain it, which all of you are doing it stupendously. Very good. Number two, we decided on what control signals are required for these different components. Number three, we decided what happens when those control signals are set to 0 and what happens when they're set to 1. Now, the instructions we are dealing with, not all of them will be setting or deasserting all of these control signals. They will be asserting certain control signals and deasserting the others. Everything will not be the same across the board. Therefore, the control unit takes in the opcode to determine which one of these signals should be asserted or deasserted given a control signal, given an opcode. Sometimes some of these control signals, we don't even bother about it, in which case we give them a don't care. What I would like for you to do next is, for the next 5 minutes, discuss with your peers, work with each other, and decide if an R-type instruction like add goes into this data path, what will be the value of different control signals? What should be the value of regs desc if I need to perform an add? What should be the value of regs write if I'm performing an add? What should be the value of ALU source? If it is an R type, ALU up happens to be 0, 1, because that's what the table tells us. What should be the value of memory, memwrite, mem2reg? Please work on this for the next 5 minutes with your peers and fill it out. Yeah.
It's not a register.
No, just
And then in worksheet is this the same?
Same.
So only 0 or 1.
0,
right?
1. Yeah.
So okay. Thank you.
Tracing the data path will also help.
Nuclear reactor ya dedi bu family sense çevirse on page o da baktı gördü family sense ki hepsi başlıyor. All right.
All right. Now, I hope you had the chance to discuss with your peers what should be the value of these control signals. So please have your attention right here. Now, first, what we are going to do is we are going to trace the path. By tracing the data path, it helps us to determine what should be the value of these different control signals. If they should be asserted, deasserted, or even in sometimes just left alone. Now, when there's an add instruction like add rs, rd is equal to rs plus rt, then this would be the data path, right? So this guy should go here. This is definitely going into there. No discussion about it. RT always goes to read the register 2, but it is the RD register that has to be written into the write register, right? Because that's the destination. So we have to set this control signal so that RD passes through. I am writing to the write register. I am writing to the write register. So you need to focus on the reg write. Now, when you're reading RS and RT, read data 1 will come out and read data 2 should come out, which should then go as the second input. And then finally, ALU will produce the result. ALU will produce the result, and it goes like this right here, and then goes through, oops. Oh, that's a sinusoid for some reason. And it goes back. That is a path. That is called tracing the data path. When we trace the data path, we are able to find out what should be the value of these different control signals. Now let's determine. Carefully observe this. Carefully observe this. RD has to pass through. What should be the value of reg dest? Cairo? 1. Very good. Very good. So for this instruction, where's the pen? Okay. All right. Let's see if I can. Oh, you know what? I can do something else. Wait. So what I can do is I can just do a 1. There you go. Nice. Now, carefully observe. ALU source, read data 2 has to pass through this mux. So then read data 2 has to pass through this mux. So what should be the value of ALU source to let it read data 2 pass through? 0. Very good. That should be 0. So that's 0. What about mem to reg? Mem to reg. We are talking about this multiplexer. ALU result should pass through 0. Very good. Excellent. So mem to reg is set to 0. What about reg write? Are we writing the register file? So what should be the value? 1. Very good. Mem read. Are we writing to the memory? Are we reading from the memory? No. So we don't allow reading. Are we writing to the memory?
Yes.
No, we are not writing to the memory either. So that's 0. Is branching involved here? No. Now for R type, ALU op 1 is 0 and ALU op 2 is a 1. And there you go. Yes. Is it a branch instruction? Yeah. So are we good with this? Yes. It should be 1 0. Okay, yeah. So thank you for referring to the table. As it happens, it should be 1 and 0. Okay, thank you. Yeah, so you please read the table and let me know if I make a mistake. All right. I'll make the slide available, so it will be there. Now, I would like for you to focus on the load word hardware. Just like how I trace the path for add instruction, I would like for you to trace the path for load word instruction and find the values for these different fields.
Right, right. Yeah, not bad. Yeah, I want to see this RS is going to go straight to Yes.
Yes, so RT is right.
Type was zero. Oh, really? Oh, really? Oh, it was 0, 1. Yeah. Okay, so well, my friend's coming. Oh, yeah. Okay. Oh, that's that was. No. 710.
You got to the town, go with that.
Oh, my friend. My cousin.
Well, my number is.
Excellent work. Very good. Very good. Okay. All right. Jazz hands again because we are going to trace path now. Let's trace the path. Now, this is how load word works. First, the memory address is computed as immediate plus RS. So RS goes in and out comes the RS value. However, the second item has to come as the immediate field. So it is a sign extended immediate. And that goes into the ALU. That goes into the ALU. Address is computed. RT is the location where we need to write. So RT has to pass through the first multiplexer, read data, whatever data has been read, that's passed through, and that is written into the right data port. So that's the path for the load word instruction. That's the path for the load word instruction. Now, when we consider regdest, it is RT that needs to pass through. So what is the value for regdest? 0. Very good. Excellent. Next is ALU source. The sign extended immediate has to pass through. So what should be the value of ALU source? 1. Very good. Next up is mem to reg. It's the read data that has to pass through. So what should be the value of mem to reg? 1 again. Very nice. Then we have reg write. Are we writing to the register in load word? Are we sure?
Yes, not sure.
Not sure? Okay, let's see what the definition of load word is. Load word is load the value from the memory and write it into the register. So are we writing?
Yeah.
Yeah, we are writing. So reg write is 1. What about memory? Are we reading the memory? Yes, we are reading from the memory right there. Reg RT is data memory mem address. So mem write is again 1. Is it a branching instruction? Is load word a branching instruction? No, so that is set to 0.
So these will be the final values, right? So let me correct me if I'm wrong. So regdest has to be 0. ALU source has to be 0, right? Oh no, it has to be 1. Mem to reg will be a 1. It is. We are writing to the register. We are reading the memory. We are not writing to the memory. It is not a branching instruction. For load word, store word, it is 0, 0, 0, 0. Perfect.
Small word is just going to make right? So
Not everything is.
Yeah, but the memorizing the one,
Yeah.
is writing the 0.
Right, right. So you have your worksheet due by midnight today. For that worksheet, now this is important, so please jazz hands one more time, jazz hands. For your worksheet, please refer to this figure. Do not refer to the processor 7 figure because that has some zero padding and all those additional things added. Just take a snapshot of this figure. Use this figure to find the values of different control signals. So for worksheet 6, use this figure to find the values of control signals, not the processor figure number 7. We are not there just yet. All right. So it's a good time to stop. Yeah. And you have to find what kind you had to create a dictionary and you use to find the value. Now you have to use the values to find it. So that's and depending on your output, each instruction will have different way of setting up. So you may have to write it down ahead of time and then just code it in.
I have a question regarding was it the add instruction for the so for the now can you give us the code for the buttons for that
Very good point. Unfortunately, we didn't have the time for that. So you would use the same code as load word and store word. But yeah, the reason is because it adds an immediate value. That is also sign extend. And it has the exactly same inputs. So ALU is technically doing the same thing for add as it is doing for load word. So you would use the same code, same ALU output. How's it going? Hey. Not sure.
Because like I was in the office in the engineering, I was saying I saw like this.
Oh, these were that was actually gifted by the alumni from Kuwait.
Oh, there's a
Oh yeah, there are a lot of people from Kuwait that have come.
really? Because like I only like I found out like there was another crazy here. I was like, I need to find that person.
Oh, okay, okay. Yeah, I mean we have had a lot of Kuwaiti students before you, I guess.
Awesome.
Yeah.
Thank you.
Uh-huh. What's happening? Are you how about this? Why don't you email it to yourself from your email client and then upload it on Windows? Yeah. Hey.
So, someone in class mentioned that the thing is supposed to write to a file, not print it out.
Yes.
This is not one of the things you mentioned when I showed it to you, my version.
Oh, okay.
Is this the kind of thing that I should resubmit it or not?
So okay, can we talk?
Yeah. Is that
He said you don't know if you're saying that's right there. That's right. Yeah, exactly. Check the ad right now. Oh, okay. No, I just want to see if it actually. How did it change? We got the same. I know. Which one? You got now. No, I'm not. I did the last one. All right.
What we do is I'm trying to understand this thing for the store word.
Right, so oops, what happened here? Why should I discarded it? So let me just end it.